So let's start. Our next speaker is Teruhisa Kadokami from Kanazawa, and he's going to talk about some observations on Amphicheirality links. Please.
Thank you very much. I'd like to thank the host and the organizers.
Yes, I should say one thing. So yes. he shared his slides in the chat. Okay, so you can look up his slides in the chat, and I also posted them on the website, on the workshop website. But he updated his slides a little bit, so so the latest version is in the chat. Okay. Okay, so please.
Yes. I attached my talk slide in chat. Yes, I like to talk about Amphicheirality links. Yes. Sorry. Yes. Firstly, I wrote references like them. The main part will be sections 3 and 4. Firstly, I'll explain my main theorem. Amphicheirality link is a link which is equivalent to its mirror image. As terminology, Amphicheiral sometimes said achiral, non-amphicheiral said chiral. We like to consider these kind of problem trefoil, right-hand trefoil and left-hand trefoil, whether they are equal or not. The same problem for figure 8 node and oriented Hopplin case. If the Hopplin is unoriented, it is Amphicheiral. But oriented case, link number different positive Hopplin and negative Hopplin. In this case, sometimes we say they are not Amphicheiral. We raise some problem, basic problems. The first, determine a link is Amphicheiral or not. The second, study invariance of Amphicheirality. The third is the minimal crossing number of Amphicheiral link, always even. Some answers are no in general, but yes for alternating links. this is Alexander Stoimenov's result for every odd crossing number greater than or equal to 15. There exists a prime Amphicheirality knot with the minimal crossing numbers C, DC. And today we show there exists two-component Amphicheiral links with the minimal crossing number 9 or and 11. They are prime one. The fourth problem is their general construction of Amphicheiral rings. We made a table of prime Amphicheiral rings with the crossing number of components greater than or equal to 2, and the crossing number is less than or equal to 11. Then I write one conjecture. Let L be an n-component algebraically split component preserving. I will explain this terminology later. Component preserving Amphicheiral ring, and n is even. Then we have the multi-variable Alexander polynomial of L equal to 0. I don't know precise answer. You may know what is algebraic split, thinking number 0, one another. We obtained I and Akio Kawachi, he obtained one result. Let L be an n-component Amphicheiral ring, and let Lij is the link number of Ki and Kj. Then if this number total link number plus n is even, then we have the Alexander multivariable Alexander polynomial of L at every variable equal to -1 case equal to 0. And in the same paper, we showed that if L is an n-component component preserving the epsilon Amphicheiral ring, and n is even, then we have the multivariable Alexander polynomial equal to 0. This is a partial answer of our conjecture. About this theorem, in 1984, Teruhisa already shows these two cases, n equal to 2 and epsilon equal to plus minus. The second case, n is greater than or equal to 3 and epsilon is minus. I will explain this, the meaning of this terminology.
Can you?
Yes.
So
yes.
I only see the first slide of your talk. Is this intended? I only see the title page. I do not see any further slides. So I see only the title on Amphicheiral links. Sorry.
now can you see?
I can see now page 2.
Yes.
Page 1.
Yes. Sorry. How about now?
I can see the first page.
Yes. Second page?
No.
No?
No.
Okay, I see. I don't use full screen mode. No. How about it?
I can see first page.
Yes.
Now I can see second page.
Yes. I use this. I explained the differences and the contents. The main parts are section 3 and 4. And this page. And I explained four problems. And I write the conjecture. Yes, I'll explain about this terminology later. I conjectured that for let L be an n-component algebraic split component preserving the Amphicheirality ring and n even, then the multiple Alexander polynomial of L is equal to 0. And in my work, joint work with Akio Kawauchi, we have two theorems. The second theorem is a partial answer of my conjecture. Yes, Totality already showed partial answer. So this theorem, this theorem it's a kind of generalization of the result of Totality. We define a scalar link and invertible link. It's an elementary part, so I'll skip to explain. Anyway, we like to confirm some terminologies and Rademacher moves and the fundamental theorem. We define the Amphicheirality ring. We like to use notation for link something, for example, L, its mirror image, we like to denote L asterisk L star. Let L be a link in the 3 sphere and the diagram of L, and let H be an orientation reversing homeomorphism of 3. Then we denote L star by we denote HL by L star. We call it the mirror image of L. Yes, as we can take as edge by this special map. So we define that L is a scalar link if and only if L is equivalent to L star as unoriented links. Invertible link, 3, 1 and X 17. Let K be an oriented node, and minus K, the orientation reverse node of K. For an unoriented link L, we denote the orientation reverse link of L by minus L. Now we define that L is invertible link if and only if L is equivalent to minus L as oriented links. For an oriented node K, the connected sum K and K star and K and K, the connected sum K and K star and the connected sum K and minus K star are Amphicheirality node. This is plus Amphicheirality node. This is minus Amphicheirality node. And for K, the connected sum of K and minus K is an invertible node. We like to explain link symmetric group. This notion due to Witten and Hyunwoo. Let L be an n-component link. And now we fix the orientation of S3 and the orientation and the we fix the orientation and the order of L. Let N be the set of elements in mapping class group of this pair S3 and link L. Phi satisfies. Phi is an orientation preserving homeo of S3, preserving orientations of orientations and orders of the order of L. This set is a normal subgroup of mapping class group of this pair S3L. now we define yes this multiplication satisfies associativity, and this is unit element, and this is inverse element of X. So we can introduce group structure to gamma n. Then the link symmetric group of L is a subgroup of gamma n. This is notation. We also denote by like them. If kappa is plus, we omit this this plus, and if an element of symmetric group is identity, we can omit it, and if epsilon 1 to epsilon n are all equal to epsilon, then we denote it by this. We define a special subgroup of gamma n, denoted by gamma n0. That is kappa is equal to plus case. This is index to subgroup, and gamma n is direct product of g over g times gamma n0. And this group, this is a normal subgroup of gamma n. We have a natural surjection from gamma n0 to the n symmetric group I. Then the kernel of this surjection is isomorphic to g over 2g to n. And more, we have this split exact sequence. So we can determine by using this exact sequence. We can determine a precise group structure of gamma n. Finally, like this, it's twisted by this homomorphism. The order of gamma n is equal to n plus 1 times n. This I forgot to say this character. And we denote gamma 0L equal to the intersection of gamma L and gamma N0. We call it the plus link symmetric group of L. Yes, we can write some problems about link symmetric group. The first one is that determination problem determine gamma L. And this second realization problem, which subgroup of gamma N can be realized as gamma L. N is equal to one case. That is the case of Amphicheirality not. We have these universal set. Gamma 1, 0 isomorphic to Z over to Z. This corresponds to invertibility. And gamma 1 is isomorphic to Z over to Z times Z over to Z. Gamma to 0 is isomorphic to the fourth dihedral group. Now we define link symmetries. Let x be x equal to kappa and epsilon 1 epsilon n sigma is in gamma L. Then we say that L is x symmetric. And in particular, if sigma is equal to iota identity, then we say that L is component preservingly x symmetric. And if x is in gamma 0 L, then we say that L is epsilon 1 epsilon n sigma invertible. If all epsilon I is equal to minus, then L is said minus invertible. And this set gamma 0 L minus unit element is not empty set. Then the L is set simply invertible. If x is in gamma L minus gamma 0 L, then L is set epsilon 1 epsilon n sigma Amphicheiral. And all epsilon I is equal to epsilon. We say that L is epsilon Amphicheiral. And if this set is not empty, then L is set Amphicheiral. Yes, we consider conditions from invariance. The first Milner's invariant, but I'd like to skip most of this part, but I like to only say linking number. Link number is very important to study Amphicheirality. Yes. So yes, this page. For an n-component link L K1 union Kn, and Li is equal to linking number of Ki and Ki plus 1. The first, if n is odd and all Li is not equal to 0, then L is not component preservability Amphicheirality. The second, if n equals 3 and all Li is not equal to 0, then the L is non-Amphicheirality. Yes, this is easy observation by using linking number. Theory 4.3, let L be a two-component link, K1 and K2, and L is the linking number of K1 and K2. The first, due to Hartley, if L is a component preservingly Amphicheirality, then the L is equal to 0 or odd. That is, L cannot be non-zero even. The second, if L is epsilon and minus epsilon and 1 to transposition between 1 and 2 Amphicheirality, then L is not equal to modulo 4. But L can be 4 times. L can be 4 times integer. There's Taniyama writes examples. This kind of Amphicheirality ring with 4n linking number for every integer n. About Alexander polynomial, let L be an component oriented ordered link. Then it is this is multivariable Alexander polynomial. This is determined up to multiplication of this trivial element. Then we denote like this, large A dot equal B implies this. Then it is well known that by duality we have this equation. Lemma 4.5. Let L be kappa epsilon 1 delta epsilon n sigma symmetric link. Then we have this equation. But this is not so strong restriction. So useful, but we cannot say very useful, useless for component preserving epsilon symmetric things. Yes, this condition is not the case. Very famous result due to Hartley and Kawauchi. The first, let K be minus Amphicheirality node. We have this kind of conditions. The second, let K be plus Amphicheirality node. Then we have this kind of condition, but we don't like to enter in these conditions. But anyway, by using these conditions, we can see non-Amphicheirality of the trefoil and non-invertibility of 8 to 17. Yes, this part is my result for link case. Theorem 4.8. Let L be an n-component algebraically split component preserving epsilon Amphicheiral link, and n is even. Then we have the Alexander polynomial delta L to t eta 1 t to eta n equal to 0, where eta I is in 1 or minus 1. Theorem 4.9. If L is a two-component algebraic split component preserving the Amphicheiral link, then the Alexander polynomial of L, two-variable Alexander polynomial L, is divisible by t1 minus 1 square and t2 minus 1 square. Theorem 4.10. If L is a two-component algebraically split epsilon Amphicheiral link, then that two-variable Alexander polynomial of L is divisible by t1 minus 1 square, t2 minus 1 square, t1, t2 minus 1 times t1 minus t2. So I thought that I write this conjecture because if a link is algebraic split component preserving Amphicheiral, then its Alexander polynomial should be very, very big. So I thought that the Alexander polynomial of L is very big or 0. So I write this conjecture. If L is an n-component algebraic split component preserving the Amphicheiral link and n is even, then we have the Alexander polynomial of L is equal to 0. And yes, I already said that joint work with Kawauchi, let L be an n-component Amphicheiral link, and then then if n plus total linking number of L is even, then we have that the Alexander polynomial of L substitute ti equal to minus 1 equal to 0. 4.13. If n is an n component preserving epsilon Amphicheirality link and n is even, then we have the Alexander polynomial of L equal to 0. This is partial answer of this conjecture. Yes, we can apply to detect Amphicheirality of these three links. Yes, we apply this theorem for 12. The Alexander polynomial of the first link 814 substituting minus 1 equal to plus minus 16. So this is not Amphicheiral. The second link is the same result, and the third one this value equal to 0, and in reality it is easy to see that this link is Amphicheiral. The condition from Jones polynomial is very clear. This is a well-known theorem that if L is Amphicheiral, then the coefficients of the Jones polynomial are symmetric. So by using Jones polynomial, 24 is not Amphicheiral. We can see it immediately. So we use mainly Alexander polynomial and Jones polynomial that we made a list of Amphicheiral link, prime Amphicheiral link with the number of components greater than or equal to 2 and the crossing number less than or equal to 11. The notation we follow Sistle's weight table. The blue one implies that it is not component preservingly Amphicheiral. For example, let us see this one. This one. This is 9 crossing Amphicheiral. And this is not component preservingly in Amphicheiral. By taking after taking mirror image, we can change, we can interchange components. And one more example, this one. This is Fleming. This is a kind of Mursky sum structure. After taking mirror image, we interchange this part and this part. Yes, their table. This is 11 crossing case. And we show that these two cases are a little bit hard to detect non-Amphicheirality. 10, 51 to and 11 and 100 to 27 to case. We could show this is not Amphicheiral by using two variable Alexander polynomial. And we could show this is not Amphicheiral by taking twofold branch covering along the second component K2. This is trivial node. Then K1 is reflected to K tilde by calculating John's polynomial of K tilde. We could show that this is not Amphicheiral. So the original link is not Amphicheiral. Yes, this is final part. For two-bridge link, yes, you all know that Comes notation. We denote it by this, and Schubert's notation. Yes. For two-bridge node K, S alpha beta Schubert form is alpha odd. That is not the case. Is Amphicheiral if and only if beta square equal to -1 mod alpha. Equivalently, there exists integers. We can take symmetrically. The second is the link case. We can take totally is same one, but yes, by calculating continued fraction, some cases not, some cases are link to component link. For example, C22 is figure 8 node, and C33 case it is two component link. Tangle sum, we denote let T and T prime be two tangles with n arcs. We denote this form by C T prime. And there are some actions to tangle T. We act an element an element of dihedral group DM. Tau and rho are generators. DM acts on the complex unit disk as tau complex conjugate. Rho rotation is 2 pi over m degree, and T star is the mirror image of T. Then let T and T be tangles with n arcs, and we take two elements x, y from the dihedral group D to N. Then we denote like this. It implies this one. And then it is equivalent to this one. So we have we call it normal form. So we denote C T star and identity T2 eta rho to K by large T eta K. Eta is in eta is 0 or 1. K is in Z over in this case 2 and Z. And we denote large Tk equal T0K and T minus K equal large T1K. This is almost a final sheet. Let T be tangled with n arcs. Then T0, Tn, and T minus K is strongly Amphicheiral. If L has this expression, then we call it a tanglesome construction of L. So we can write one problem where Amphicheiral link is it made by a tanglesome construction. We confirmed with Kobatake. Any prime Amphicheiral node with the minimal proximity number up to 12, and prime Amphicheiral link with the minimal proximity number up to 11 are made by tanglesome constructions like this. This is just a part of the table. Yes, this is almost final sheet. For future study, the first one is that define and study Amphicheirality for links in general three manifold, including the case of virtual links. The second, you use more refined invariants such as Hilbert-Floyer homology, Kobanov homology, and so on. The third one, study the relationship with the cosmetic surgery problem from then surgery problem. Then surgery theory. The fourth one, study the tanglesome construction problem. Is it affirmative for for prime case, and is there counter example in general? I don't know. This tangle sum construction just corresponds to even crossing number problem. The fifth one, find fundamental moves among different tangle sum constructions of an Amphicheirality link. Yes, thank you very much for your attention. Alex. Can you hear me, Alex? In chat, you said something. No. Hirasawa-san wrote. Yes.
Okay. Thank you very much.
Thank you
for your talk.
Thank you.
So may I have a question?
Yes.
Go ahead.
Okay. So I'd like to confirm some points. So, is your conjecture still open or not?
I don't know. I don't know progress. So for me, now still conjecture.
Still conjecture. So in the theorem 4.13.
Yes.
So you have the assumption that the algebraically split. Is it necessary for your conjecture, or there are some counterexamples?
Epsilon case, this condition case automatically algebraically split. Yes.
And So one more question. So is it necessary? So the condition that the component preservingly is necessary? So,
yes.
For your conjecture?
Yes. In my table, yes, some links are probably this link. The link number of this link is 0, but the Alexander polynomial of it is not 0. And this is not a component preserving Amphicheiral.
Is it Amphicheiral?
Yes, it's Amphicheiral, but not a component preserving. And its Alexander polynomial is not 0.
Not 0.
Not 0. Yes.
But algebraically split link.
Yes. Link number 0. Yes.
And
sorry, this is not correct. For another example, this is not linking number.
Yes.
0. Sorry. Probably another example. Maybe this or this. There are examples. Alexander polynomial is not 0 and linking number 0 and Amphicheiral. Then it is not a component preserving Amphicheiral. Maybe this. Maybe this one. This is linking number 0. And its Alexander polynomial is not 0.
So is it still difficult to solve your conjecture? So even when we assume that all components are trivial.
I don't know well now. So I like to use more refined invariants such as Higad-Fourier homology, Kobanov homology, and so on, or look precisely to fundamental group or something, or Alexander module or something. Yes.
So do you believe that your conjecture is true?
I don't care. There is a counter example. So yes, I little hope my conjecture is true.
I understand. Thank you very much.
Thank you very much.
Okay, so if there are no further questions, then let's thank Teruhisa again, and we will finish this evening with Mikami's talk. Okay?
Thank you.
Thank you very much.
Thank you very much. See you.